during the presentation.
Very good. So thank you very much, Pierce and other organizers, for having me here. This is really a great conference. Also being in London, if the weather is always like this, I should probably apply for the lectureship at UCL. I think that's what we all wish. So this talk is really about the physics of materials when they're driven coherently by light. So it's a little different than what most people in condensed matter research, or in the, let's say, in the mainstream of condensed matter research work on, and it's a little different from the physics that most people in laser physics work on. So I'm always kind of a bit of a weird speaker at basically any conference I go to. Let's see. So the general idea is the following. You have a material that has a certain state and a certain phase. This is some energy as a function of order. And you irradiate this with light, a coherent electron, and I'll tell you more about the light in a second. And so what you want to do is to control the order of the system dynamically as a function of time. So now this time axis could be short, could be long, depending on the details of the pulse that is periodically modulating the material. And so broadly speaking, we want to create a new form of non-equilibrium light matter coupling axis that sort of complements what is being studied extensively over all these sort of adiabatic changes of static parameters. So this is what we're trying to do. So there's a number of goals that you can set for yourself if this is what you hybrids. The important point here is that the light field, or let's say the term of the Hamiltonian that keeps into account the interaction of the light field with the material, is of the same order as everything else. And so the idea is that in this hybrid of light and matter, you may find new emergent physics that is interesting, and that is not simply a perturbation. So the goal of these experiments is not to probe the ground state of the system, but to create a new state of aggregation, if you wish, in presence of this coherent drive. So I won't talk about Floquet engineering here, but there's people think about a Floquet expansion in studying, trying to understand the dynamically driven Hamiltonian in terms of a time-independent Hamiltonian in presence of a time periodic drive. This is the second thing that we try to do, is to try, and actually I'll tell you a little bit about some progress that we've made in this area, try to find potential applications in the high bit rate devices, or high bit rate, let's say terahertz. So above the, say, tens or 50 gigahertz of the dominant high frequency technology. This is something that we tell funding agents. This may or may not be true, actually. So people do say that we can, by studying this, we can make some statements about what the ground state was before I excited it. I don't think this is really always true. And in some selected cases, you can do that. But an example that I make for students in my group is, if you build a Ruby laser, you need to know about the ground state of Ruby, but by running a Ruby laser, you will not learn, you're not doing spectroscopy of Ruby. You study a completely different driven phase of Ruby. And so whether this teaches us whether this type of stuff teaches us a lot about the ground state of cuprates is really questionable, at least in my view. So what lies beneath these activities is basically nonlinear optics. So we've had nonlinear optics for about 60 years now. There's been, even by a very restrictive definition, there must have been a dozen more Nobel Prizes that are based in one way or another on nonlinear optics. But it's fair to say that 99.9999% of all experiments that are based on nonlinear optics are performed in the visible. And this is because lasers operate well in the visible and they don't operate well in the far infrared. And so what people have been looking at for many, many years are responses of materials to strong light that is of order EV or more. Okay, and there's a number of things that you can do in nonlinear optics that have been done over the years. One thing is to use materials to change light. You come in with a red beam and you get a blue beam out. You can also use light to probe materials nonlinearly. You can look at surfaces. You can look at flowers, various ways. Depending on the polarization, you'll get different. You can do Raman scattering, do many things. And then there's this. This is what we are talking about: using light to control materials. So generically, if you use an EV, remember, 1 electron volt is 14,000 degrees, and you have a material at, say, 300 Kelvin, so that's 25 millieV. So generically, if you use a laser pulse in the near infrared, and let's say you have some ordered phase of a material here, yes.
Okay, the meeting being recorded.
Come again?
So we can see the title if you can okay.
Oh, okay. Let's okay this. How do I okay it?
There's a blue button, okay.
I understand there's a blue button, okay, but it's not on my screen.
You have to exit. You have to unshare, escape. Okay.
He's not seeing what we're seeing.
No, I know.
Click escape.
Click escape on the computer.
Yeah, now you can see it. Yeah. Now
I haven't said it's okay. You see there's a blue button.
Oh, yeah. Okay. This guy here? Yeah. All right. Very good. Sorry, guys.
Oh, wait, no, the share.
Press F5, I think.
No, the share.
Oh, I need to reshare. Sure. Okay. What am I sharing here? This guy. Share. Okay. Yeah. Okay. Yeah. Very good.
On Zoom, it's now the wrong thing.
Is it?
You should hold the entire desktop.
Got it. Share.
No. Maybe that's right.
No, this is correct, isn't it?
Yeah.
Want to bet? Look at this. Yeah. Okay. How am I doing?
Okay.
Yeah. All right. So here's my ordered state, which, as we said, has some intrinsic strength, which is of order room temperature. So it's weak. And now, if I irradiate it with the visible light pulses that I usually use for nonlinear optics, basically I'm depositing 20,000 Kelvin per particle. And so generically, almost always what happens is that I start from an interesting ordered state and I create a boring disordered state. And that's most of what we do. So basically I take water, which is, let's say, an interesting state, and I boil it and I make a gas. So that's really not great. What we would like to do is the opposite. We want to take water and make ice with a light pulse. So that's what I'm not the first person to say this. People do laser cooling. You have many ways of creating order in driven systems, but this is really what we would like to do. So you need to be a little bit clever about this. This is your order. In reality, what you would want to do is, and this will be a theme over my talk, there will be another excitation, which is coupled to the order that I want to enhance. And I will be driving or saturating this excitation. This is in the spirit of the Overhauser effect, if you wish, in NMR. And this will generate order, will polarize the state. That's the goal. To do this, you need to do nonlinear optics at energy scales that are somewhat commensurate with the excitations of the system that I want to manipulate. And so what I need to do is to generate nonlinear or strong fields of light. And I define arbitrarily a strong field as one that has an electric field that is a megavolt per centimeter or larger, let's say. And I want to do this at frequencies that are below 10 millieV, say. So, or below 100 millieV. So this is where all the phonons are, or at longer wavelengths, this is where all the manifestations of quantum order are found. So this is some sort of generic Mexican hat potential. So One of the problems that you have is that if you try to build a laser that generates strong fields in the far infrared, you will generally not be able to do this. And the reason for this is that basically all the lifetimes are wrong. If you generate states that are only a few tens of millieV far apart from one another, everything will decay by electron phonon coupling because because basically electron boson coupling goes with 1 over c to the fourth, and the speed of phonons is much lower, or the density of states is much higher for phonons than for photons, and so you will not laze generally. So there's 2 strategies for this. Up to a few years ago, you could use a terahertz per electron laser, and so you wouldn't get much beam time. These are large, expensive, but in the newer generation, so what we have all learned how to do is how to set up some tabletop sources which start from a visible laser and use nonlinear optical down conversion to generate far infrared light pulses that are intense enough. So this seems like a complicated setup, but it's you know, it's $500,000 and a couple of students and a lot of assistant professors these days that if you visit their labs, they have setups like this. And by the standards of quantum optics, this is not an especially amazing system. So now we could do here what was done at X-ray at terahertz per electron lasers, and now get into this driving regime for materials. So most of what I'll tell you about, yes, sir.
What has been the technological driver? Why weren't people doing this before?
Because, well, there's a couple of reasons. Number one is when I was a graduate student, this laser took the whole table. And you'd start aligning the laser at 9 a.m. in the morning, and by 7 p.m. you'd start measuring. Right? Nowadays, you come in the morning, press a button, laser warms up, and then you can worry about all of this. Point number 2 is that most people that knew how wouldn't know why, and vice versa. People that knew why didn't know how. So there wasn't really that many people that were interested in doing these kind of things. So I think that's part of the. Laura says no. No.
We can argue later, but what's the original laser?
It's a titanium sapphire femtosecond laser, which nowadays you buy at Safeways for, but used to be really the whole heart of the experiment, right? Yeah, yeah. So let's say that you have a material and you have a light field. It's this light pulse is resonant with a collective excitation of the system. In this specific case, it will be a phonon. Say you drive this phonon. Let's say you're at 0 temperature, and you deform it coherently. So your field is, say, 110, 20 megavolt per centimeter. Let's imagine that the polarizability or the Born effective charge of this mode is large. And so the displacements will be of order 1 to 10% of the unit cell. Why are you laughing?
Oh, I'm laughing because you're using the Fourier transform of white light when you're speaking with the laser.
Say that again?
Because I'm laughing at the cartoon.
What's wrong with my cartoon? It took me a while.
That's not a laser. That's the Fourier transform of white light.
No, that's a short pulse with 1, 2, 3, 4, 5, 30% bandwidth. No, this is a short pulse at far infrared frequencies, and the bandwidth is about 20% because it's 5 cycles, right? So, but you know, many of these phonons are overdamped, so I'm actually matching. I mean, a phonon doesn't swing many more times than 5 cycles, so that's about right, actually. And so the important thing is that these atoms, depending on the polarizability, will be shaken at amplitudes that is far larger than the displacement, than the thermal displacements that are explored by fluctuation. So you're really exploring a new physical regime.
Are these sort of uniform, or are they quite different depending on layer and layer?
Well, let's say that you have you impinge over a bulk.
Mm-hmm.
Now you will be resonant with the phonon. You will absorb, or you will drive over a skin depth. This, depending on the polarizability, the skin depth will be anywhere between a micron, let's say 100 nanometers to 10 microns.
This is still bulk.
Definitely bulk. Definitely bulk. Yeah. So over. So the Poynting vector goes like so. The electric field goes like so, and you'll you'll be screened about one skin depth, let's say 1 micron. So this new node, like, let's see. So we try to do these experiments. So my compatriot, Enrico Fermi, is thought to have said that when you're an experimentalist, you can do one of two things. If the results confirm the hypothesis of the theory, you've made a measurement. If the result is against the hypothesis, then you've made a discovery. So I don't know what it was for Fermi, but in my experience, there's two possibilities. If it confirms the theory, the result is trivial, otherwise it's wrong. So I will be going through a set of examples. The first part will be about trivial physics, and the second part will be about wrong results. So let's start with the trivial, because at least that would give you some degree of confidence. That's, that's going to be the first part of the talk. Again, the goal was going to be to take water and make ice by doing the appropriate shaking. And there's a number of strategies that you can apply. One that I will not talk about, but I would like to emphasize, and that's what we started with, is to take a material that has some form of competing order that stifles some order that you want to resurrect. And so you will use a light field to quench the competing order, such as, for example, stripes in a superconductor, and make the other order appear. So that's something we worked on, for example, in some stripe cuprates, where we would drive, I won't tell you about this, but this has been a long story, where we would drive certain modes to, say, melt stripes and then let superconductivity either emerge or try to emerge. So this is now work also done by other groups. Again, there's other examples of this. People melt certain charge density waves to generate other charge density waves, or they melt superconductivity to enhance charge density waves. Anyway, this has now become a bit of an industry, and that's one approach that you can have if you want to generate a state that is more ordered than the ground state. The second thing that we've been looking at over the past few years, I will tell you something about this now, is take situations in which you have a staggered form of order. So let's say you take an antiferromagnet and you would like to make it a ferromagnet or a ferrimagnet. So what you will try to do is do experiments in which you will uncompensate, say, the crystal fields around each one of the two sublattices and try to make the material ferrimagnetic in one direction or in the other. This is basically what's at equilibrium. This is done with strain, and it's called the piezomagnetic effect. So this is actually a drawing, but this is Anki Disa, who was a postdoc with me, who is now at Cornell, showed that you can take cobalt fluoride, which nowadays is discussed as an ultramagnet, but it's really also an antiferromagnet where the two sublattices can be uncompensated by some optical equivalent of the piezomagnetic effect. And this is now finally what I'm going to tell you about in the first recent experiment, where we take a material that is not globally chiral, but where we use some form of deformation of the lattice to induce what I will discuss in terms of ferrichiral order. So let's see. Alpha quartz, beta quartz. Let's say that I want to take a light pulse and turn alpha quartz into beta quartz, or do something else and turn alpha quartz into beta quartz. Very difficult, because you need to break so many symmetries, all the roto translations. I mean, there's many, many things that you need to do. So basically, if you want to take alpha quartz and make it beta quartz, you melt it, and then you recrystallize it and hope for the best. But there's a number of materials which can be described as antiferrochiral. So this is BPO4, which is piezoelectric, which is not chiral in general, but within the unit cell has both hands, which perfectly compensate each other. So if you try to rotate, if you measure gyration with a light field, you'll see no chirality. But there's two fragments of the unit cell that have opposite chirality. So it turns out, this is actually work that is done by my wonderful student, Paul Jang, who is part of our Max Planck International Graduate School. Michael Fesch, the two people in my group, Paul Gordani, my colleague in Oxford, who was helping us a lot, and Philip Moll and Karsten Putzke, who are new Philip is a new director in our institute that is helping us shape these materials. In any case, this is the equilibrium structure of BPO4. Turns out that there is a single phonon which you can displace in one or the other direction to make either the right hand bigger or the left hand bigger. So if you can take this system and displace this optical phonon selectively to one direction or to the other, you can make one hand bigger than the second. So remember, you don't want to excite that with light, because if you excite this with light, what this thing will do is will make right hand, left hand, right hand, left hand with zero average, and nothing's going to happen. What you want to do is to find an auxiliary excitation, then they somehow rectified into this ferri-chiral phonon channel. Right, so that's what I was trying. Oh boy. This was this phonon here. So what you want is to have an auxiliary excitation that couples to the structure. I apologize for this. So you want to find an auxiliary mode, which I call QIR, which I'm going to drive, that couples to the ferri-chiral mode, which I call here QB, and displaces it. Right. So let's think about the equations of motion of this nonlinear phonon coupling. You have an IR phonon mode, which in principle doesn't do anything except that it's coupled to the ferri-chiral mode through this term. Q square, which is the mode that I'm driving here, times QB, which is the ferri-chiral mode. And then the other terms in the energy are the two linear energy terms of the two springs and the coupling between this mode and the laser. And this quantity is the Born effective charge. It tells me basically how charged this mode is. And so now I can write two equations of motion for these two phonons. And so I will have a light field that shakes the QIR mode backwards and forwards, which by virtue of the Q square Q coupling will displace the second mode as long as this first mode is shaking. So it's basically thermal expansion, but only applied to two volume preserving optical phonons. So this is the drive, and this is the rectified mode. Yes, Prime. Yeah. Very good question. Hold for one slide. So you can now calculate. So this is Michael Fechner, who's in my institute, and he looked at the nonlinear phonon coupling of BPO4, and he says, well, really, there's a doubly degenerate mode. This doubly degenerate QE A and B, one polarized like so and one polarized like so, which couples in this Q square Q channel to the ferri-chiral mode, one with positive sign and one with negative sign, which means that if I pump like so, I'm going to enhance the right hand, and if I pump like so, I'm going to enhance the left hand. So this is an experiment now, actually relatively simple experiment, where you pump this vertically polarized auxiliary high frequency mode, and then you use a second pulse that measures polarization rotation in this putative light-induced chiral system. And here, if you, I won't walk you too much through the details here. There's basically two components. One is that is an induced birefringence, which I don't want. And secondly, there is a chiral component, which is this optical activity. But as long as the first phonon is being shaken, the ferri-chiral phonon will be displaced, and I have optical activity. Now I can, instead of pumping along the z-axis, I can now pump along the a-axis, and I get the opposite chirality. Turns out that this is actually a pretty large effect. If this is the rotary power of quartz, and it's 100, the induced rotary power in either direction, goes with the square of the drive electric field, because it goes with Q squared, and then it gets in the neighborhood of the rotary power of alpha and beta quartz. So that was very nice. At some level, this is a trivial experiment, really. It's very interesting. But there's a number of things. This is what we're working on right now. Of course, this thing is only a structural type of chirality, but in principle, if I can use similar methods via some form of electron phonocoupling or spin lattice coupling, I might be able to imprint some chiral texture in subelectronic system by controlling the lattice. Another thing that we're trying to do is to try to couple this phonon to strain. There should be a term by which the right chiral should couple to a compressive strain and the left chiral should couple to a strain in the opposite direction. This is basically the equivalent of an Archimedes pump, right? The functional form, the functional quality of a chiral system is to couple a rotation to a translation. So I ought to be able to find a system. These are some of the things. There's a lot of other things. In principle, maybe one could look at reactivity at surfaces, et cetera, et cetera. So this is a relatively simple way of controlling chirality that might be used in a number of things. So that was the first trivial thing I wanted to tell you. The second one is to use these methods to try to build ultra-fast memories. As you know, one of the bottlenecks in memory storage and manipulation is basically speed. What you want to take, memories are now either, let's say, ferroelectrics or ferromagnetic. There's a big push to try to drive, say, these memory units between two states at faster and faster speeds and with lower and lower dissipation. If you take a ferroelectric, this is some sort of, I found it on Google before, some sort of depiction of a ferroelectric. If you try to switch between this and this with an electric field, you're basically going through an incoherent process where there's a lot of dissipation, domain propagation. What you would like to do is really to do it with a single phonon, drive it backwards and forwards and minimize dissipation.
And that, so
yes.
This other curiosity.
Yes.
But one of the simple molecular lasers is ammonia molecule.
Yes.
It works exactly like this. The nitrogen, in some sense, can tunnel through the plane of hydrogen, so being one side of the other. Wouldn't that be just a fancy laser?
Say that again.
Well, if you look at those two configurations, they're separated by a gap. And you can imagine resonantly driving it back and forth.
Yeah.
With a period that will actually give you the frequency of the laser. That's how ammonia lasers.
I mean, it's not exactly that vibration that lasers. I mean, it's ammonia laser is a rotational laser, actually. Yeah, so it's a slightly different, it's on the manifold around.
But is that similar idea?
Not exactly. And because the reason is, to give you the bottom line, if you take a ferroelectric and you try to drive the soft mode to go from this way to the, what will happen is that the frequency of the mode will change by an order of magnitude whilst you're rotating it. So very good people have tried for decades to rotate the ferroelectric polarization. They have failed because I think you need, as I will show you, there's better strategies. Not that easy to just sort of rotate the mode. Yes. Okay.
So you're saying Feynman in his lectures in physics, he wasn't completely honest with how an ammonia laser works, because that's the example he uses, and I think he calls it an inversion. Which
I mean, ammonia laser is a rotational laser, at least according to my book.
Right.
Yeah, I mean, it's a 1 terahertz.
It's the example he uses. He probably simplified it, but that's why many theorists know this is something and think.
I see. Okay. Now you put me up against Feynman. So
different particle also talks about it as being inversion.
Also, remember the ammonia mode is Raman active, has no dipole, right? So it's I don't think it's even IR. So that doesn't sound right. The same. Yeah.
I'm going to dig into that.
Okay. Yeah. Right. Anyways. Okay. So what you want to do, you have a laser pulse. You want to do 3 things. You want to switch it in less than a picosecond and not much slower as you do with electrical drives. You want this to be non-volatile. You want to switch it to the right, leave it to the right, then come with another pulse and switch it to the left. So you want to do it at 1 terahertz, so you want to leave it for 2 days. That's what you need, right, for this. So we got really interested in this problem because of the nonlinear phononics, which we thought was going to save the planet, and we thought we could do anything. So we figured, why shouldn't we be able to switch a ferroelectric? So this is how this works. You take lithium niobate. We take lithium niobate because it has an enormous nonlinear optical coefficient. So it's very efficient. It has 2 states, plus P and minus P, and this is what you would like to do. So this is now your energy. for the deep in the ferroelectric state. Lithium niobate has maybe 2,000 Kelvin. I don't know what TC is, but it's very high. And so you're deep in the, and what you want to do is rotate the polarization between the two states. So nonlinear phonon, so I already explained to you how this works. You shake one phonon, this is the soft mode, which at low temperature is not really soft, the polar mode, let's say. And this is, you want to use a high frequency auxiliary mode. You shake it, you couple, you displace the polar mode, and you basically tilt the potential from left to right. What's great about this is that the sign of this force depends on the sign of QP. So if I'm in the red position, I get a force toward the blue. But if in the blue position, I get a force toward the, so that's good. And so this was actually, Roman Mankowski was my PhD student, actually developed all of this. And then we sort of had a number of refinement of this, but basically you could try to study the perturbed nonlinear phonon response of a ferroelectric. So it looks like so. It turns out that if you do the experiment, and I won't belabor too much how we measure the polarization, is basically by measuring the phase of the second harmonic generated by a second time delay probe. You can really start, now you start from the blue state, from the red state here, which is 0 polarization. You apply this pulse and then it switches to 180, or you start from the 180 and it switches to 0. The problem is that after it's done switching, it goes back immediately. So it fails royally on the non-volatile requirement. So this thing is basically useless. Because every time you, and the reason for this is that if you switch a domain of a ferroelectric and you're surrounded by the ferroelectric, which is pointing in the opposite direction, what you will generate are uncompensated charges at the edges of the domain, and this will switch you right back. So basically a waste of time. I mean, it's very nice because this gave us some degree of confidence that we could manipulate these ferroic orders, but as far as applications go, this is really not what one should be going to. The same thing, although people don't tell you, is also when people apply short pulses to ferromagnetic states, they have the same problem. You have uncompensated sort of dipoles or magnetic dipoles, and unless you drive them very slow and you can get rid of them, it's really sort of a problem. So most recently, we've been looking at other ferroic systems. So this is my ferroelectric state. I'm plotting here different types of order and the symmetry that they break. A ferroelectric state breaks inversion. A ferromagnetic state breaks time reversal. A ferrotoroidal state breaks both. And then there's a ferroaxial state. There's this new type, at least new in my mind. It doesn't break either in inversion or time reversal. So a ferroaxial, you should think about this as a vortex of ferroelectric dipoles. So imagine you now have ferroelectric dipoles that wind around like so, or they wind around in the opposite direction. So this is a state that breaks neither inversion nor time reversal. And by extension, it will not have uncompensated charges. But by extension, I also will not be able to manipulate it because it doesn't couple to any field. So the conjugate field of this thing is some curl of E. It's an axial field, right? So, right, that's it. So we work on this rubidium iron molybdenum oxide, which is basically, imagine all the octahedra that kind of rotate around. And so all these have a dipole that winds in either this direction or the other direction. One way, so the first thing you need to find is a way to measure this state. You want to know whether in the ferroaxial plus or the ferroaxial minus. And it turns out that if you measure second harmonic generation with circularly polarized light, there is a dichroic signal. Imagine, if you have all the ferroelectrics that wind like so, or all the ferroelectric dipoles that wind like so, the circularly polarized second harmonic would be different if you're right circular or left circular. And this is actually true. So these are actually long measurements. But if you measure left circular minus right circular, and this is the ferroaxial transition is known by X-ray scattering, is around 190 Kelvin. You can now look at these A plus domain, A minus domain. Again, these don't couple at linear order. to any field. All the IR mode connected to this, so the mode connected to this rotation is both non-IR active and silent in Raman. So it's difficult to see, but at higher order, you can measure this. And so in principle, you could probe it. Now you want to switch it. That's a very good question. I'm going to need something. Free energy, something. I don't know, interfacial energy, volume energy, the usual stuff. I mean, there would be some ratio of the interfacial energy, probably strain, and all right, anyway, so now we want to use a light pulse that doesn't couple to this order, and we want to switch it from right to left. So it turns out that if you can take it, this is St. Paul Jank that did that, who's actually a pearl of a student. This is, good thing that the Americans don't take these kids anymore. After he's like a third-year graduate student who's in Oxford. Anyways, so basically the idea is that if you find a system with two doubly degenerate modes and you drive them in quadrature, what you will do is that you will move atoms in circles. So the cations will go like so, and the anions will go like so, okay? What you will be able, so now if you consider this field that is now constructed completely artificially by the fact that you're moving atoms in circle, there is a field which is the cross product of Q cross E, the electric field that is being applied, where Q is the coordinate of the phonon, or alternatively, Q cross Q dot, if you wish, yes.
It's not coupling to IR or Raman.
This is another mode. It's not the ferroaxial mode. This is another mode.
Another mode, okay.
Remember, you have the piston that shakes, which then now wants to displace the mode. Very good point. What we want to do is to couple to this A2G mode, which is silent, through another field anharmonically. Okay? I have a little animation later for this. So anyway, basically, if the ions are rotating in circle, this engineered field, Q cross Q dot, or Q cross C, will either be positive or negative, depending on which direction the phonons are rotating. And there will be a nonlinear coupling between the ferroaxial mode and this cross product of the two. So, and basically, so you can calculate the equations of motion of this. This used to be my ferroaxial order as a function of the amplitude of the A2G mode. Now I apply this high frequency bias with a circularly polarized light field and the Q cross E of that field. So this is the doubly degenerate mode that I'm driving in circle. It's an EU mode, of which there's two. So I can engineer a field that rotates. And now this will apply a force which will displace and tip this otherwise degenerate pair of states either to the right or to the left. And so this is basically an engineered axial field that couples to the ferroaxial mode. These are again equations of motion calculated by Michael Fechner, whom I introduced before. There is a threshold above which I potentially can switch these between these two states. So above a certain fluence, I should be able to do this. All right, so this is what you are asking, Laura. So I'm moving the auxiliary pendulum in circle. And this is coupling to this this is coupling to the QA2G mode. What's very nice about this is that according to the equations of motion, when you're done pumping, the mode stays there. So it should be non-volatile. So you stop pumping it, and the state should stay there. Then you can come with a pulse of opposite rotation, and you should generate a force in the opposite direction. You stop pumping it, and at least what the theory says is that so you'll be able to really use the circular light. Right. Okay. Yes.
What are the two states? What you call left and right.
Left and right. Okay. The domains. Okay. This was my vortex of dipoles. There, you see, there's plus minus plus minus plus minus minus plus minus plus minus plus. These are the two states, right? I have these vortices of dipoles.
But there's a dipoles like physical distortions?
Yeah, they're like little ferroelectric units They just wind around. Hey, no, something like this exists. It's amazing. Okay, anyways. So this is now Paul did this experiment. So he comes in the morning, he launches one single pulse at low fluency in the A+ domain, which he has identified by doing the dichroic second harmonic. He pumps it in below 10 millijoule per square centimeter, which is approximately 10 megavolt per centimeter fields. Nothing happens. These are single pulses, right? And then when above a certain threshold, he switches the domain. This is the dichroism of the second harmonic, and I go from the A+ domain to the A- domain. Then he goes for lunch, comes back, pumps again, same direction, he stays there. So we only checked up to 6 hours, but nothing changes. Then he's in this state. Let's see, is he in this state? Okay, whatever. He takes this state, takes the opposite polarized, single pulse, and above 10, no, he's in this state, sorry. He uses the opposite polarization, about 10 millijoule per square centimeter, it switches. There's a little bit of a coercive field here that we're trying to understand. But so this is now the experiment. You come in, you switch it with circularly polarized light, you generate the A+ domain, then another pulse, A- domain, A+, A-, A+, A-, even seems to be getting a yield. And he gets a little bit better at every, really the bottleneck on how fast we can prove that we've switched is the time that it takes to probe the pulse. So it takes actually almost an hour to determine that the domain is right or left. But this is really a rewritable, non-volatile, ultra-fast memory, or at least some. And you can tell that this is very interesting because nature didn't want to send it up for review. And so it's really, okay, sorry.
What temperature is this at? And that's amazing how long the lifetime is.
Very, very good question. The temperature that is at is below 190 Kelvin, but just below. 190 Kelvin is the thermodynamic transition temperature, and this is, I'm going to say 90%. If you go far deeper, this thing gets stiffer and stiffer, and you can't switch it with these fluencies anymore. So anyways, so that's the other thing that I want to tell you here is that this is also another thing that Paul explained to me. He said, well, when you go above TC, you're going to have some form of para-axial system. The system really doesn't have two stable states, but I should be able to use the light field to polarize my non-ordered state into an axial state. And actually, so these are the equations of motion. Instead of having the double well, I have something that on average doesn't really break a symmetry. But if you drive it, you're going to switch to the right or switch to the left. Your energy, because of the Q cross Q dot times A to G term which is basically pushing this guy down. And you can see now that if you redo the same experiment, you can generate an axial state above TC. So this is Folke-induced axial, a state that only lives for a very short time. And so this is kind of ties everything up. And we're trying to understand, so this only happens immediately above TC. And we're trying to understand exactly how the effect scales as you cool it to work. There's lots of interesting things that are coming up. You can train the axial state if you cool it in a circularly polarized pulse, not unlike what you would do in a magnetic state. Really a lot of fun. Yes.
Investigated how this relaxation changes as you approach TC from above. Should you take?
With only what we have investigated is the threshold as a function of temperature. We're trying to find some form of photosusceptibility of this effect, and that seems to almost diverge, right? But not in enough detail. Yeah, but you can. It's on the archive. So if you're interested, where is it? So if you're interested, you should take a look at the data. Okay. Okay. This is the. So I want to say one thing. During COVID, we wrote this review paper with Ankit, and the idea there is that really one should view this nonlinear phonon control as some sort of dynamical equivalent of the many beautiful techniques that people are developing in equilibrium to control the functionality of materials, either by twists. I mean, we're actually sort of worrying of whether one could simulate something similar to this by using a dynamical perturbation, interfaces, train, et cetera, et cetera. So this really comes in as a new form of dynamical structural control. So how much time do I have left?
Half an hour.
Very good.
Yes.
Very good. If somebody wants to ask me something more about the trivial, do, because I'm moving into a completely different topic, which is really rather more surprising, has to do with superconductivity. And yeah, I would like to.
So how generic is it? How difficult is it to find such an auxiliary mode that will work and couple strong enough?
Yeah, I mean,
the
DFT people are pretty good. People that,
how far you can tilt, right?
So basically, if you take a smart DFT theorist, they're usually pretty good at calculating frozen phonon. So what they will take is they will take the mode, the auxiliary mode that I want to drive. They will calculate how these distortions along this coordinate will couple to the mode that you want to displace. There's also a whole story about higher order nonlinear phonons. I only talked about the lowest order. Anyways, so the answer is you talk to a smart DFT theorist and they will tell you. Even in complicated materials, they're usually pretty good at getting the phonons and their couplings. Meaning in what I meant complicated, in systems that have strong correlations and difficult magnetism, usually the phonons are well captured. Yeah. Yes. Yes.
Can you figure out which phonon drives conductivity? You can couple to if I make a supposition that some phonon, but all this coupling is just group theory. Right?
So yeah, the problem, what I've been told, yes. Oh yes, the question is, can you use this driven phonon approach to understand which phonon is important to drive a particular superconductivity experiment? Yes.
Problem, right?
Remember, so this is something that Demler explained to me and made me feel very ignorant. In BCS, the problem is not the amplitude of the phonon, it's the noise of the phonon, right? What you want is right? So if you now drive a classical phonon coordinate to large amplitudes, that does not tell you about the important term that you have in BCS, which is really, Is that making sense? When the second guy jumps on the mattress, you're not interested in how far the mattress goes down, but how elastic it is, right? And so what you're interested in is how much the mattress is fluctuating, not, right?
But you're only sensitive to optical phonon, right? I mean, a lot of the phonons are acoustic phonons.
Yeah, absolutely. One of the reasons why, and I will tell you later.
A lot of superconductivity.
A lot of BCS, I mean, a couple.
All the carbonics are optical.
It's true though. If you take aluminum, it's an acoustic phonon, right? So that can be done in that way. Yes. Somebody, yes, please.
What you're basically in BCS, only phonon frequency. It's a virtual phonon. It's only in BCS, it's a virtual phonon.
Yes.
Phonon frequency.
Yes.
That matters and not phonon density.
Yeah, that's right. So this was just to okay. So strategy number 3, if you want to take water and make ice, is to take a material that has fluctuations in the normal state above the thermodynamic transition temperature that are large and that are, that has large precursor fluctuations that are beyond what you would expect from an ideal approach. So we've looked at, for example, strontium titanate, which is a paraelectric with very large ferroelectric fluctuations. We've recently looked at yttrium titanate, which is a D1 system in which large orbital fluctuations basically suppress a mean field TC of 100 plus Kelvin to about 20 or 25 Kelvin. And then we've become interested in the fluctuating. So I'm now referring back to Laura's talk yesterday, what is these fluctuating superconductivities throughout the pseudo-gap phase and the existence and non-existence of Cooper pairs or preparing and whether one can use this fluctuating state, one can manipulate this fluctuating state to enhance superconductivity. So this is a summary of the things that we've done over the past few years so that you can take strontium titanate, at finite temperature, drive it in a certain way and induce a ferroelectric order by driving. You can take this suppressed ferromagnetism in yttrium titanate, and you can make a photoinduced ferromagnet. And then there's this business of photoinduced superconductivity, which is what I'm going to tell you about, which is probably the most controversial thing that we've been working on, and in trying to understand if you take a fluctuating superconductor and you drive it coherently, whether you can enhance the coherence or induce superconducting-like coherence above TC. Right. So the strategy behind this business is to take a material, again, I refer back to Laura's talk yesterday, there's a number of materials in which if you measure the Nernst effect, so as most of you know, the Nernst effect is basically the measurement of a transverse voltage in presence of a magnetic field and a longitudinal thermal gradient. And so basically, there's a quasi-particle contribution to this effect. But if there are vortices that are present above TC, these vortices will diffuse because of the thermal gradient and will give rise to a transverse voltage that is clearly non-quasi-particle in presence of a magnetic field. And so there's pioneering work done by Ong's group, of course, in the cuprates. And this is the famous T onset, which is really a statement about your signal to noise in your ability to measure. The Nernst effect is kind of a negotiable edge of pre-existing superconducting fluctuations. Then there's all this class of materials of kappa salts. This is my Oxford colleagues have shown a few years ago that you can have these very large non-quasi-particle Nernst effect here close to the Mott insulator of these kappa salts. And then there's the potassium 3C16, which we did the experiment the opposite way. We excited it with light. We showed that you could enhance the signatures of superconductivity above TC. And so we went back and we measured the Nernst effect, and we found a large non-quasi-particle Nernst effect above TC, far above TC. And this is actually very interesting. It would be a completely different story. It's very interesting because this is an isotropic three-dimensional superconductor, and yet has signatures of very large superconducting fluctuations above TC, showing that there's more than BKT physics in this problem. All right, so you take these materials, and what you want to know, so this is now your material, which is your candidate material to show photoinduced superconductivity. You use a mid-infrared pump pulse to drive a particular phonon, which you choose based on a combination of calculations, but also sort of maybe intuitive argumentation. And then you use a terahertz probe pulse. And if you're above TC, you start from the optical properties of a metal, which look like so. So this is now, these are the optical properties of a Drude metal here in red. You have a real part of the optical conductivity, which is the in-phase response of the current to an electric field, which has a finite value at zero frequency, and then it rolls down at the scattering rate. Apologies here, this is the gap, but there should be a scattering rate 1/tau here. And it has an imaginary conductivity, which is the response of the current, which is in quadrature to the applied electric field, so the inductive response, which in the Drude has a peak at the scattering rate. Now, when you cool the material below TC, what you find is that in the real part of the conductivity, there's a gap opening and a pole at zero frequency. And the presence of this pole at zero frequency is manifesting a divergent imaginary part of the conductivity. Long story short, you want to pump a material, start from the red and go to the blue. And if you go to the blue, then I'm going to argue that gives you a necessary but not sufficient condition to state that you have discovered a light-induced superconducting state. So in the three classes of materials that I talked to you before, this is the most beautiful data. This is kappa BDT. You start from the red Drude state above TC. This is not now my sigma 1 that rolls down at the scattering rate, and sigma 2 that actually goes to zero at zero frequencies. You pump a certain phonon and you open a gap in sigma 1, and you create a 1/omega divergence in sigma 2, indicative of the presence of a pole in sigma 1 at zero frequency. And then TC is something of order 10, 15 Kelvin, but you go all the way to 50 plus Kelvin and you find signatures. Look at this gap that gets smaller and smaller and smaller, and you find signatures of this light-induced superconducting like state. This is potassium doped C60. You start in the metallic state. This is the Drude. You open a gap. In this specific case, there's been a lot of discussion. It turns out that the size of this gap is a bit negotiable. But nevertheless, you all, depending on, regardless of how you fit the data, you find gapping and divergence sigma 2. And in YBCO, which is what I'm going to tell you about today, you will find gapping, not gapping, depending on whether you look along the insulating C-axis or the AB planes, but you definitely find this divergent 1/omega omega response of the conductivity. So these are all features of the superconducting-like state, and I'm going to tell you a little more what I mean by that.
On the case of copper BPT,
yes,
what changes as you go from left to right?
In the ground state?
No, just you have a sequence of
temperature. Sorry, temperature.
Temperature.
Yeah, sorry, this is bad. You just immediately above TC, or you're above a. You go for. I mean, just to give information here, you have a normal state that is coherent, and here you end up in some sort of dead metal state where which you cannot resurrect anymore somehow. Okay, so now let's take this material, YBCO. You pump it. So the mode you decide to pump is this mode that these are the superconducting planes in the AB axis. This is the C axis. And what we focused on was a specific mode in which the position of the apical oxygen is modulated backwards and forwards, and the distance of the apical oxygen to the superconducting planes is modulated. The reason for this is that there is ample evidence that in equilibrium, the position of the apical oxygen correlates with TC. Just said simply, you have this 2p orbital that is, and these are the 3D x squared minus y squared planes. If the 2p oxygen orbitals hybridize strongly with the d orbitals of the plane, you have a more three-dimensional state, and superconductivity gets worse. Whereas there are some arguments that if the apical oxygen is far away from this, superconductivity will be reduced. In any case, there is evidence, experimental evidence, that TC correlates with the distance of the apical oxygen to the planes. So what we thought is that if we shake the apical oxygen up and down, we'll be able to add some sin omega t to the in-plane electronic properties. This is the transition when you cool the material below TC in equilibrium. Along the C-axis, the material is insulating. Basically, doesn't, there's very small conductivity in equilibrium gaps, and you have this imaginary part of the conductivity diverges. When you're photoexcited, you get exactly the same divergence of sigma 2, indicating that you're creating a state that is similar to a superconductor. Now, recently, we've looked at results, good Lord. In plane, this is what you see in equilibrium. You go from this state to the divergence sigma 2, and you go from this state to the gap opened superconducting state. When you pump it, you generate something that kind of looks like the divergent sigma 2, although it's smaller, and you open the gap. So
just check for clarification that this is now unrelated to what you mentioned earlier on about melting of competing order.
Yes, this is not competing order, except unless you go to YBCO 6.6, where there is also a competing order. Actually, the answer is I don't know.
So it's not
I mean, there might be some spin order. I don't know. This is not targeting the 1/8 stripe phase of single layer cuprates. Come again? This one is 6.48, the specific one. So it's about maybe 10% doping or something. Yeah. This is too much information. Basically, lifetime. If you pump, now we've learned how to pump with longer and longer pulses. We can make this thing live many picoseconds. Okay. This is all great. The reason why this is very controversial is that in C60 and in this one, when you measure the disputative light-induced superconducting state as a function of base temperature, you find that this correlates exactly with the pseudo-gap phase, which means that you can generate this state that looks like a superconductor all the way to room temperature and higher. And so, this is why everybody gets very emotional about this. And or maybe let's say that the what's the word, that the burden of proof is raised immediately to a large level. Now, it turns out that what I just told you is a sufficient, but not, sorry, is a necessary but not sufficient condition for superconductivity. And let me tell you why. This is this is sigma 2, the imaginary part of the conductivity for a superconductor. It diverges like 1 over omega. Basically, it's inductive transport. So impedance is proportional to omega. If you take let's now take a metal that has very, very high mobility, so very low scattering rate. Sigma 2 will look for all the frequencies higher than the scattering rate, basically like a perfect conductor, so it will be inductive. It means that the charge is accelerated when you apply an electric field. But then when you reach 1 over tau, this thing will roll over. But now let's take a superconductor that only lives for a timescale tau, and let's plot sigma 2. And so the transit superconductor kind of looks like a Drude metal, where the lifetime of the superconductor goes into the equations for the scattering. Furthermore, if you're measuring only over this region, if these scattering rates, now we can discuss whether the scattering rate is reasonable to imagine that a scattering rate of a metal can be so low. But, it becomes a little bit of a subjective statement where you say, well, this thing looks like 1 over omega just because I'm measuring in the same range where also accelerated quasi-particles might look like 1 over omega. Now, for full disclosure, this 1 over tau would have to be extraordinarily small. But then again, who knows, right? It's a driven phase and maybe it's coherent or maybe you have, anyways. So that's the reason why this is necessary but not sufficient. The way you should solve this problem is you do the following. When you do, usually what you do is if you take a material, you cool it down and then turn on a magnetic field, you have the same problem that you have here. Right? If you turn on the magnetic field, after you've cooled this down, what you will measure is the 1 over omega response. You look at magnetic field exclusion. But if you cool it down in a magnetic field, I'm reminding things that everybody knows, but I had to, when we started working on this, I had to go through the textbooks again. If you cool it down in a magnetic field, then either the material is a perfect conductor, in which case the magnetic field will be stabilized, or the material becomes a superconductor, in which case the material will expel the magnetic field. So if I do the same thing, I embed my normal state in a magnetic field, I photoexcite it, and then the two possibilities are it's either a transient superconductor, therefore the magnetic field will be expelled, or it's a transient high mobility metal, in which case the magnetic field will be locked in place, even more rigid than it used to be. So these are two radically different things. So this is work done by my two wonderful PhD students who, for many years, I thought maybe this thesis was a little too difficult. This is Sebastian, who's now at UT Austin. Giovanni, who's also a postdoc in Hamburg, working on cold gases. Michele is a staff scientist in Hamburg, and Gregor now, who actually comes from cold gases, and was a postdoc with me, is now at UPFL on the faculty. So here's the experiment. You take the material in the normal state, you apply a small magnetic field below HC2, 10 millitesla or a few millitesla. You photoexcite the material, and then you look for expulsion of the magnetic field, right? So you want to go there, and what you want is to use a Gauss meter that measures maybe either on the edge or immediately above to measure whether photoexcitation expels the magnetic field. So the only problem that you have is that your Gauss meter needs picosecond resolution, nanotesla precision, micrometer spatial resolution, and most importantly, room temperature operation. So of course, one can imagine of using squids, but they don't work at room temperature. You could imagine using NV centers, but they're slow unless you do some clever tricks. Maybe nanotesla precision is not a brain surgery thing, but it was hard enough for us. And they need to have a high spatial resolution. 10 minutes, perfect. So what we did was we took a magneto-optic material where you could measure the Faraday effect. So now the Faraday effect is an effect by which if you go through a magneto-optically active material, With a pulse, you'll have a polarization rotation. This is either in transmission or twice the polarization rotation in reflection that is proportional to the basically the magnetization inside the material, but let's say the magnetic field. Because you want this to be fast, you cannot use a ferromagnet because this will depend on the precession of the magnons. So you use a diamagnet, and the Verdet constant that gives me this rotation drops by many orders of magnitude. And yet, if you're careful enough in the way you measure this polarization rotation, you'll be able to measure the magnetic field around here. Now, so this is my YBCO. Remember, these are the superconducting planes. Turns out that YBCO is very difficult. Okay, I'll tell you later why. But really, really, really what you would like to do is pump from the bottom and probe from the top. And the reason for this is that you don't want to be irradiating. Sorry, where are you here? You don't want to be irradiating with your pump. You want your sensor to be nowhere near where your pump pulse is, right? So this is the way we do this. Then we put this gallium phosphide, which is my diamagnet, with enough Verdet constant and enough speed to encode polarization rotation. We cover it with sapphire. We pump the YBCO and shake the apical oxygens and create a moon-shaped region, which finishes with a lithographically defined edge here. And then we use a second pulse. Where is the second pulse? And then we use a second pulse that goes here on the edge to look for an enhancement in magnetic field on the edge of the Fock-induced state. And then we try to measure this as a function of pump-up delay, et cetera, et cetera. So, yes?
What do you expect if you take like a piece of aluminum? I'm just trying to
understand. Yeah, let me show you this. Okay. All right, let me show. So let's just solve this problem, the magnetostatics of this problem. So the problem that you have, this is now, everything is conspiring to make this difficult because you pump from the top. And so you generate the skin depth. But then when you measure the Faraday effect, because of the symmetry of the Faraday effect, and the fact that the magnetic field is along this direction, you need to use this geometry, which means that this is what my students call the pizza geometry, has the worst demagnetizing factor you can think of. So you want to go here on the edge and measure a changing magnetic field. So now, for this case, and if you have 100 micron wide puck or pizza, and 1 micron thick, going back to the question before of how deep my excitation is, for a 10 millitesla, all right, what I am plotting here is now a calculation of how much will the magnetic field change immediately outside the material for different numbers of diamagnetic susceptibility. Okay, this is of course a type 2 superconductor. It turns out that for chi's of minus 30%, so large numbers, and for an applied field of 10 millitesla, you should observe a change of about 10 microteslas on the edge. Does this answer your question? So if you have a type 2 superconductor and chi is minus 30% and it looks like a pizza, it's 10 to the minus 3. That's the answer on the edge. Yeah.
Okay, but sorry, you travel superconducting vortices to start with, or are you below HC1?
On the edge of HC1.
But what I'm trying to understand is
yes.
Why should magnetic field change at all? What are you changing? I give you type 2 superconductor.
Yes, I cool it down, let's say in equilibrium.
And then
it becomes super. No, I haven't shined light yet. What I want to calculate now is, let's imagine that I start with a vegetable and I turn it into a superconductor. This superconductor might have a chi of 10 to the minus 4 or might have a chi of minus 1. If chi is minus 1, then the change in magnetic field on the edge will be 10 millitesla. But if chi is even a little bit less than minus 1, then the change will be 10 to the minus 3 because of the geometry. However, if the material is a perfect conductor, okay, then the change in magnetic field will be 100 picotesla, so 6 orders of magnitude smaller. So this is if the response is static, which it isn't. But let's just start and try to sort of reference ourselves. And so now I'm going to do the experiment. We're going to pump this guy use the fast Gauss meter here. And if I'm good, I'll measure 10 microtesla here on the edge using my, so I start above TC now, I photoexcite, and I want to see the field lines being expelled by my photoexcited state. So there you go. You pump it, this is now at 100 Kelvin, 2 times above TC. And what you find is what you find is that the magnetic field measured on the edge goes all the way to approximately 10 microtesla, which in a static, if you believe in magnetostatics, should be equivalent to a quench of the susceptibility from 10 to the minus 6 to minus 30%. So it's one such diamagnetic state in equilibrium can only come from a superconductor. Okay. When you go to room temperature, you get this. So chi, the quench of chi gets quenched to something like 5%, minus 0.05 to minus 0.07. Again, far larger than what a perfect light-induced perfect conductor would look like. There's a number of checks. You should, I need too much detail here, but this thing, if it's a Meissner effect, should be completely independent on the incoming polarization angle. We've also measured, this is too, not that important. The important thing is that this was the optical conductivity determination up to T star, and this is the magnetic field expulsion that goes all the way up to T star, telling you that these two guys are approximately the same. We've only looked at this effect in one doping level. So what we're trying to do now is try to map the distribution of change in magnetic field everywhere. We don't necessarily own, we're not, of course, satisfied with just measuring the deformation of the field lines on the edge. But to do this, you need a C-axis cut thin film, which is approximately 2 microns thick. This is work we're doing with my colleague, Philip Moll. So we're using a focused ion beam. We're planning to use a focused ion beam. This is the experiment we're trying to do. Pump from the bottom and probe from the top. From the top here, sorry, there's another. Yeah. And so in principle, we should be able to measure a reduction of magnetic field here and give us a better idea, are there vortices, are there things that are happening? So this is the PhD thesis of Han Gu and Jesse. I'm going to say it again. This guy was starting at Harvard. He didn't get a visa. So again, silver lining of an awful situation. So Jesse's with us for a little while, whilst things get sorted out in the US. So he's really a very talented young man, and he's so these guys are making a lot of strides in cutting these lamellae with focused ion beam. Okay. Let's see. I don't really have much time, do I? I mean, I have like another 70 slides, so we can just stop. So most important thing is, so does this teach us something about the ground state? That's something I said at the beginning. So Patrick seems to think that it does. So basically, Patrick Lee came to me and said, look, you've proven what I've been saying all along, right? And basically the idea according to Patrick and now working with Marius, who used to be a student with Eugene at Harvard, basically what they're saying is that YBCO is already superconducting within the body layers. And so I'm not really doing what I'm saying I'm doing, but generating phase slips. So there's this paper on the archive, generating phase slips within the body layers that are simulating sort of this large expulsion of magnetic field. This is one of the reasons why we need to sort of measure overall positions. Yeah, that's about it actually, because I was going to tell you a whole story about potassium dope C60, which I won't tell you. And right. Yeah, let me just go to the end. Sorry. I just apologies. Yeah. I just threw a bunch. I've taken 30 slides away this morning, but I just had a few things. So we observe colossal transient diamagnetism in the floating state of this. So this is now superconducting light squared. Whether it's really a it's not even clear. You know, I'm just going to say something here. I've regretted calling this a light-induced superconductor in the first place because, of course, it helps you to tell people, listen, this is important, big deal. But then you're really bound by a very strict definition of what a superconductor is, et cetera, et cetera. So what we have is this light-induced state that has a very large mobility, clearly, has a very large diamagnetism, has a critical current. If you had waited another half an hour, I would have told you about measurements of critical currents, which were done in C60. I mean, there's a lot of, this is kind of superconducting, actually, transiently. So this guy lives for a nanosecond, this guy lives for 5 picoseconds. Is this useful? Probably not. Is this interesting? Very, at least to me. There's a deep connection between the ground state of these bad metals that will become superconducting when you cool them down. And now when you drive them periodically, they seem to acquire these very strange non-equilibrium properties. So this is really new physics in a driven system. And so I would say this is my conclusion, right? I think Audrey Hepburn said this, and I thought it was pretty good. So I sort of added it for the end. Thank you for your attention. Okay, let me go back. This was final one. Some discussions.
I have two things to say.
Yes, sir.
First of all, in my undergraduate class, we do a demonstration in which we take copper and we cool it down to liquid nitrogen temperatures, and we watch and we put it on top of a big magnet, and it gradually comes down. It takes about 3 seconds. And so you'd need to have a resolution. If you wanted to see that in the frequency domain, you have to have a resolution that would resolve down to the Hertz level to actually see the difference between copper at nitrogen temperatures and a superconductor. And so a thing lasts for a picosecond is nowhere even close to copper at 70.
It's definitely not close to copper. Yeah.
So I don't, and that's just a remark.
I understand. Right? I understand. But that's what happens in the close to the ground state when you apply a magnetic field. Now let me tell you a story here. Just let's do a Gedanken measurement.
I just did do a Gedanken.
No, but I'm gonna offer you. This is gonna get good. So sorry for the people. No, you're gonna be good. So people on Zoom. The question is really when you measure the Meissner effect, it takes forever. How can it take a picosecond? What are you talking about, basically? Right. Okay. So now then we can compare notes. Let's imagine that I have a material with an applied magnetic field, and now I quench let's say that you have a cold gas experiment, and I do a quench in which chi goes from 0 to -1, right? What will happen is that the magnetic field will be deformed, and that's set by the speed of light, I would say. And so I have a dB in the spirit of the Huygens principle. I have dB dt at the edge of the sample, and now this dB dt will radiate for a picosecond like an antenna. And this is what we see here, right? You see a magnetic field pulse that propagates from left to right from the edge of the sample and propagates out there. So let's go back to now your situation. As you cool the material below TC slowly adiabatically in a magnetic field, you form the vortices. These need to drift. They carry the magnetic field, et cetera, et cetera. I think that the electrodynamics is completely different. I'm trying to say, but there's nothing wrong with quenching the diamagnetic susceptibility in a picosecond and observing changes that take a picosecond. Does that help or answer your question?
No,
or
I was just pointing out that copper at nitrogen temperatures looks like a superconductor. Just on the time domain.
I'm sorry. You're not talking about.
Sorry, no, so it's my point is that if you were to optically probe copper at nitrogen temperatures, you'd need something that could resolve things.
Sorry, just one second. If I cool copper in field,
just take it.
no.
Just take
If I, no, let me finish. If I cool copper in a magnetic field, it will not look like a superconductor.
If I take a sheet of copper,
yeah,
dump it in a bunch of liquid nitrogen,
yeah, and then you
turn on. I take a magnet and I put it on.
Understand? That's called the zero field cooling. If you field cool copper, you'll get nothing.
Yeah, but that's true. But all of your experiments are not in the DC. They're all
so what?
Finite frequency.
Let me just say it in a different way. I am a material. I'm in the middle of a field. Right? I become a superconductor. I either am a superconductor, in which case I expel a magnetic field, or I am a good conductor, in which case I oppose changes in magnetic field. And so that will be true at picosecond timescales also.
If you send radiation into copper, which has a frequency, inverse frequency of 1 picosecond, then of course it doesn't penetrate. Okay. On that timescale, radiation doesn't penetrate because of the skin effect. And so,
what do you mean it doesn't penetrate because of the skin effect? Of course it penetrates. Speed of light divided skin effect. Takes picosecond. I mean, it's a speed of light divided 1 micron. One micron divided speed of light, whatever. But
maybe we move on.
No, but the most no, just a second. This is important. What you're saying is not true.
Okay.
So if I turn a material into a superconductor and in a magnetic field, I can very well tell whether it's a superconductor or a metal.
Sure, but if you have a transient effect that lasts 1 picosecond, there's no difference between probing things in the frequency domain or not. It's a 1 picosecond lasting effect. You can't tell if you turned it into a superconductor. It's a response at the 1 picosecond time scale.
And it probes high at 1 terahertz frequency.
Sure.
Yeah.
Yeah. Good. But my point was that currents to A on a time scale of seconds in copper at 70 Kelvin.
Absolutely not. What you're saying is not right.
You can watch the puck come down like this. It just gradually it hovers for about 3 seconds.
Come again?
It's diamagnetic on a time scale of 3 seconds.
That's Lenz's law.
Of course, Lenz's law is what.
No. Just 1 second. Sorry. If the magnetic field is applied before you cool it,
I understand.
Then nothing is going to happen. You need to turn on the magnetic. The reason why it floats is that you will not want to see a
experiment doesn't do that.
What do you mean it doesn't do that? Of course it does that. You are exciting a normal material in a magnetic field, and you're observing the normal material generate an enormous dB/dt, right? So a good conductor doesn't like dB/dt, right? So if you quench, right? Let's got some more.
A good experiment would do a control experiment with such a good conductor and compare the two.
90% of my experiments don't work. So I have
buckets. My second remark wasn't connected with.
Okay, very good, very good.
The first part of it.
Yes.
Which is that you're using circularly polarized light to add angular momentum to your systems and excite them in exotic states. Yeah. I wondered whether you thought about using vortex beams instead.
You mean to move the center of mass of the beam?
Well, no, to bring
high angular momentum in the phase front.
Yes.
Have I thought about it? Not really. Have I heard about this? No, so not really. Actually,
these are photons that carry angular momentum
yes. But on relatively long length scales, though, right? It will be a length scale larger than lambda, I suppose. So you really need some.
I'm not pretty sure actually what the length scale is. How small you can.
I mean, if you have a phase front, you can't generate perturbations of your phase front on length scales. That's the diffraction limit. You cannot change a phase front with a gradient that is higher than lambda.
No, it's true that they're larger objects. Nevertheless, they deposit
absolutely.
large amounts.
Absolutely, that would be very interesting actually. Mostly probably in things like superconductors or things that have interesting rigidities at long length scales, I guess. So we should talk more about this. Yeah.
We have a question. Characterizing HC1 of your samples.
experiments and then doing the experiments in bottom below.
Yeah. Yeah, so we have actually, the point is that HC1 along the C-axis of the cuprates is a very small number, is a few millitesla, and then the signal is small enough that we just need to get Q. We sort of do the experiments kind of at HC1. If you go far below HC1, then the noise is such that then we would be having a different conversation. I understand, but the gallium phosphide will have a polarization rotation that is proportional to B times the Verde constant, which is a very small number. So a factor of 5 in B buys me a factor of, what is it, 25 in acquisition time. And this experiment takes maybe 5 days per curve. Come again? The problem is that the Faraday effect doesn't see fields in the plane. Remember the Faraday effect, you want a pointing vector and the magnetic field along the same. So we're trying to get better, but this is where we are. Yes.
Yeah, my suggestion is we have one last question because then we need to move over to the poster session. Or maybe yours plus one student question if you have one.
Thank you. So what if you did the other orientation, that you, instead of the AV planes going this way, do it this way?
Yeah.
Because we do know from lots and lots of experiments
that it destroys.
Does scale with the CUO distance.
Oh.
Lots of neutron scattering.
In plane.
In plane.
Yeah.
I can share that with you. But
I understand. The problem that you have is that the phonons are screened in plane. So they are difficult to drive because you have this high mobility plane. So what you will be coupling is mostly, in other words, the phonon resonance will be shorted by the quasi-particle. So it's very
difficult. It's up your alley.
Yeah, but I can't go against physics. Right? No, the answer is I haven't tried there's probably certain materials in which you can negotiate how much. So we've done that pumping in the plane in the strike phase. We've used in-plane pumping to destroy the strikes. Yeah, so one should try to modulate that in-plane mode also. Yeah. Yeah,
you were certainly right that the second part was more controversial than.
There you go. Have you ever seen that?
Do we have any last quick question? Otherwise, we can continue on the way to the posters.
Very good.
Yeah, let's thank Andre.